Okay, dear students, so far so good. Now what comes next is the third question of the workout part. You are given this function 3x squared minus 12 into x plus 1 over x squared minus 2x minus 3. So different questions are raised based on this function. So let's pass through them all. So the first one is to determine the domain. Clearly, as you studied in the class, the domain of a rational function is any real number, except values that makes your denominator 0. And because of this, the denominator here is x squared minus 2x minus 3. So the domain is a set of any real number except values that can make this what? 0. So we need to solve what x squared minus 2x minus 3 equals 0 is. And this is the same as this one. Just think of two numbers where their sum can be minus 2, their sum can be minus 2, and the product minus 3. The numbers are minus 3 and 2. So the sum of minus 3 and 1 makes minus 2, the product makes minus 3. So let's look for those values that can make this 0. So clearly from this it is 3 that makes this 0, and minus 1, you see, 0. So the set of all real number except 3 and minus 1 can be the domain, okay, the domain of the function. That is to say, you are free to take any number in place of x. You can have a defined output, but you are not allowed to put 3 and minus 1 in place of x, because when you are using these two, 3 and minus 1, everything goes to be meaningless, okay? That is the idea. So the domain is obtained in such a way. Next, you are asked to find the x and y intercepts. Simple. As you are sketching the graph of a function, the x-intercept is nothing, but it's a place where y is 0, right? So at x-intercept, our y, which is f of x, must be 0. So you have to assign f of x to be 0 and look for the 0 of the function, okay? So as you are doing that, the 0 of the function, look, this is 1, so you can apply crisscross multiplication. So 3x squared minus 12x times x plus 1 equals 0 can come. But as you know, 3 is a common one here, so you can take it out. So 3 into x squared minus 4 can come, and then x plus 1 equals 0 follows. So from this, try to look for those values that can make this 0. The numbers are, you see, 2 and minus 2. Basically, 2 and minus 2 are obtained from the first bracket expression, because x squared comes 4 when x is either 2 or minus 2. So that 4 minus 4 turns 0, you see, and the whole can turn 0. Here at minus 1, you see everything again goes 0. So our x-intercepts are 2, minus 2, and minus 1. So we do have 3 places when we can have these x-intercepts, okay? And next we need to determine the y-intercepts. So the x-intercepts are in terms of points are as you see. And when you come to the y-intercept, students, at the y-intercepts we do have x being 0. So just assign x to be 0 in our expression. So f of 0 is going to come, right? So y, which equals f of 0, is going to come. I directly substitute 0 here. Minus 12 times 1 divided by minus 3 can come, and this makes 4. So along the y-axis at, you see, a point x0, y4, the graph crosses the y-axis, okay, the y-axis. So the y-intercept is at 0, 4. So now we are, you see, talking about the different nature of this function. And let's proceed again. The next one is, you see, to find the existing asymptotes. And to find the existing asymptotes, first what you need to do is you have to simplify this. As I tried to explain, this is nothing but it is equivalent to x plus 1 times x minus 3, but x plus 1 can be cancelled by x plus 1, and x minus 3 is going to remain. So the numerator is 3x squared minus 12, and the denominator is x minus 3, because already x plus 1 is cancelled. And these two are identical for whatever real numbers in their domains, except at you see minus 1, because at minus 1, 0 over 0 can't be 1. Hence, these two are the same. Anyway, these two are the same. So sketching the graph of this is the same as this one, except at minus 1. There at minus 1, we do have a whole, because minus 1 makes both the numerator and the denominator 0, okay? So now we have this expression, but when we divide this by this using long division, look, we can have 3x plus 9 plus 15 over x minus 3. You see, students, just apply long division technique. You will obtain this to be the quotient, and the remainder will be 15, okay? How do you know that? Look, remember, the 0 of x minus 3 is 3, so put 3 squared here, 9 times 3, 12, 27. 27 minus 12 makes 15, so the remainder is 50. I just have applied remainder theorem, but you can even apply long division technique, no problem. Anyway, 15 over the divisor x minus 3 comes, so upon the division of these two, you can have this. So look, what you can understand from this is you can identify the asymptotes here, okay, in a simple way. So as x goes to infinity, what's happening? As x goes to infinity, look students, as x goes to infinity, the right one approaches to 0, because the denominator is increasing. Dividing a constant by a large number, you see, tends to get closer to 0, so no more this expression, but this again, you see, enlarges. So as x goes to infinity, you see the graph or our function f or y, you see, approaches to 3x plus 9. You see, 3x plus 9. It has to be from above. The reason is because we are having plus sign here. You see, as this function approaches to this asymptote, it is approaching from above, because this is plus. Even though this is a very small number, it will be added to this one, okay? It will be added. So it will be 0 point something like that. So it will be additional input for, you see, these to increase. Because of that, you see, the function gets closer to the asymptote from above. So this is one idea that you need to know. And so the function has an oblique asymptote of y equals 3x plus 9. You can also tackle this by going to minus infinity. You will come across with the same output, 3x plus 9. See, oblique asymptote. So the oblique asymptote is y is 3x plus 9. And when you go to the next one, look, minus 1 is the 0 of the numerator, the denominator, hence we have a hole there, right? We have a hole at minus 1, f of minus 1. So as you are evaluating f of minus 1, you don't need to use this, because at minus 1 this is not defined. Instead you have to use this one. So at minus 1 this makes minus 4, and this is minus 9. 9 over 4 can come, right? 9 over 4. So at minus 1 and 9 over 4 we have a hole, because minus 1 is a 0 of the numerator and the denominator, guys. What happens as we are approaching to 3 from above, from the right side? As you are approaching to 3 from the right side, look here students, as you are approaching to 3 from the right side, this is actually a small number, a certain small number can come, 9 times 9 plus 9, 18, but as you are coming to this, approaching to 3 from the right, you see, and deducting 3 from it enables you to have a very small number here, and dividing a constant positive number by a very small positive number enable us to have infinity, okay, infinity over here. So positive infinity indeed. So positive infinity plus some other positive number, you see, is going to be a large positive infinity. So f goes to infinity. So this shows you that there is also a vertical asymptote at x equals 3. You can also have analogous approach for this one. As you are approaching to 3 from the left, 2.999 may be considered, as you are putting 2.99, something like that over here. A negative output, a negative small number is going to come, negative infinity is going to appear, and deducting a certain positive number from seen minus infinity is nothing, but it is just considered as taking a spoon of water from the ocean. So this is minus infinity again. So from this you can understand that, you see, x equals 3 is a vertical asymptote. So the asymptotes are already obtained, as you see. Now having this into account, what follows is the sketch. Having all this into account, you are asked to sketch the graph of the function. So basically, in order to sketch the graph, these by themselves are enough. So what you need to do is, you see, you need to have x and y axis as usual, and try to label those x-intercepts, y-intercepts, and the asymptotes. Try to draw the asymptotes, the two asymptotes, the oblique asymptote y is equal to 3x plus 9, and the vertical asymptote x equals 3, and using that we can sketch the graph of this one as follow. You see, the graph looks like this, students. Look, here it is. You see, students, let me just explain. The vertical line, as you see, this one is yx equals 3, and this is considered to be the vertical asymptote. As can be shown, the oblique asymptote is y is equal to 3x plus 9. So the graph gets closer to these lines. As you see, it is going further and further. This is how you can know.